So today, the first exercise that we are going to consider is we are going to derive Solow model in continuous time, okay? The law of motion and steady state levels while allowing population to grow and technology grow, okay? So now we are considering Solow model where population and technology is growing, okay? So Douglas production function is given for us. Now, output is equal to capital in the power of alpha times effective labor in the power of 1 minus alpha. Where did we get this technology? I showed you in the lecture. The original that equation that we used is like output technology times capital in the power of alpha times labor in the power of 1 minus alpha, right? So in discrete time, we mark this A as if it is A in the power of 1 minus alpha. In order to make our output function as given as labor augmented production function, okay? Labor augmented production function. So now, we are saying that labor is growing, which means change in labor with respect to time is equal to growth rate of labor times labor itself, right? Or change in labor. Or in other words, in order to find the growth rate of labor itself, then we have to divide change in labor to labor, which is going to give us this growth rate of labor, okay? And now it's not the only thing that's growing. Now we have another factor, which is technology is growing, right? So change in technology with respect to time is now equal to growth rate of technology, let's mark it with G, times technology. Okay? Change in technology. In order to find the growth rate itself, we have to divide change in technology to technology itself, which is going to give us growth rate of technology. Okay? This is what we have. Now we are going to derive the law of motion of capital per effective labor, okay, in continuous time. So before deriving, let's find out what our output per effective labor is equal to, right? So our output function is given as capital alpha times effective labor in the power of 1 minus alpha. In order to make it per effective, we have to divide both sides to effective labor, yes? To effective labor. If we divide both sides by effective labor, then it will give us our output, okay, per effective labor is equal to capital in the power of alpha times, let me write it as effective labor in the power of 1 times effective labor in the power of minus alpha. I can write it, right? Over our effective labor, which has a power of 1. So we can cancel these two equals, and then it's going to give us capital in the power of alpha times effective labor in the power of minus alpha, or it is equal to capital over effective labor in the power of alpha, or it is equal to capital per effective labor, okay? Capital per effective labor. So this is it. So what we need is this one, the capital per effective labor, okay? So now let's derive the law of motion, Solow equation. So step one, number one, when we derive in continuous time that the law of motion with and without population growth, yes, we consider it what our per capital per worker is equal to. But now, because now we have technology which is growing included, we are going to consider what our capital per effective labor is equal to, which is equal to capital stock over effective labor. Right? Okay? Then what we did say in the second step, we took natural log from this equation. Right? Natural log. Once you take ln from this equation, then you will get natural log of capital per effective labor is equal to natural log of capital minus, in denominator, natural log of technology plus natural log of labor. Right? Then, after taking natural log, then we took first difference, right? From this equation with respect to time. If you take first difference with respect to time from this equation, it will give us to take first difference from all factors given. So now, if I take first difference, so a change in capital per effective labor or with respect to time times first difference of ln x is equal to 1 over x, or in other words 1 over capital per effective labor, right? Equal change in capital stock with respect to time times 1 over capital stock minus change in technology with respect to time times 1 over technology plus change in labor with respect to time times 1 over labor. 1 over labor. Which one? This one? It's in the brackets. It's in the bracket. I did not open. If I open the bracket, it will be minus. So now, let's again write those changes with those symbols, so not to repeat writing all of them over and over again. So now, change in capital per effective labor over with respect to time is equal to per effective labor change with dot, okay? Change in capital stock with respect to time is K dot. Change in technology with respect to time is A dot. And change in labor with respect to time is L dot. So now let's rewrite this equation once again. So which is going to give us change in capital per effective labor over capital per effective labor is equal to change in capital stock over capital stock, right? I'm rewriting. Minus change in technology over technology plus change in labor over labor. Population is growing, technology is growing. So now, change in technology over technology is equal to growth rate of technology, right? Change in labor over labor is equal to growth rate of population, labor. So now it's equal to G, and this one is equal to M. So now we can write it as change in capital per effective labor over per effective labor. Capital is equal to change in capital stock over capital stock minus G plus M. Yes? Okay. So what did we do in this step? Once we reached this step, we considered what our change in capital stock is equal to, right? Change in capital stock is equal to investment minus depreciation. It's investment minus depreciation. which I showed you last week in the graphic, okay? So now if you plug this one in here, then you will get that our change in capital per effective labor over capital per effective labor is equal to investment minus depreciation over capital stock minus delta, G plus N. So now if we divide it by K, so then we have it now. Capital per effective labor change over capital per effective labor is equal to investment over capital stock minus, now we have delta left, right? If I take in the bracket, so now delta plus G plus N. Can I write it like this? Yes, right? So now it's equal to this one. So once we reach this step, what did we do? We multiplied both sides of this equation by denominator in the left side, which is capital per effective labor. If we divide both sides by capital per effective labor, then we are going to take change in capital per effective labor is equal to investment over capital times capital per effective labor minus delta plus G plus N times capital per effective labor. And from here we know our capital per effective labor is equal to capital per effective labor is equal to capital stock over effective labor. So now we will place it in here, then and it will give us capital per effective labor change equals saving rate times Y over capital stock times capital stock over effective labor minus delta plus G plus N times capital per effective labor. So now this numerator and denominator is same, which we can just cancel, right? What we have left in here, right? Saving rate times Y over effective labor, or Y over effective labor. Yes? Saving rate times Y over effective labor. It is, what does it give us? Output per effective labor, right? We can write it as change in capital per effective labor is equal to saving rate times output per effective labor minus delta plus G plus N times capital per effective labor. So this is that Solow equation, the law of motion. The law of motion. Okay. So during the lecture we discussed once economy is growing with a given effective, capital per effective labor. It is, and with a given production function. And that, investment and depreciation, it will reach one point, which we call as steady state level, right? And we said that this economy, this function, okay, is with population and the technology grows, it will reach steady state level, okay, where our capital per effective labor will reach that steady state level. And it will reach, if capital, it's going to reach the steady state level, that our output per effective labor is going to reach steady state level. And at this point we have this consumption, which is for consumption per effective labor in steady state level, right? Okay. So now we have to find steady state level of capital per effective worker. Once the economy reaches steady state level, after this point, okay, where investment and depreciation is equal, right? capital is not going to change anymore. Capital per effective labor is not going to change. It's going to remain same. So which means that our change in steady state level is equal to 0. So now, in order to find the steady state level, okay, so it's going to be 0 equal saving rate times y hat minus delta plus g plus n times capital per effective labor in steady state level. We know what our per capita y is equal to, right? Where we already derived. Our per capita y is equal to, capital per effective labor, output per effective labor is equal to capital per effective labor in the power of alpha. So now we can write it 0 equal to saving rate times capital per effective labor in the power of alpha, which is going to be in steady state level, minus delta plus g plus n times capital per effective labor in steady state level. So now you can easily derive it, right? If we take this factor on the left side, delta plus g plus n times capital per effective labor star is equal to saving rate times capital per effective labor star in the power of alpha. So if we divide both sides both by the factors that we want and simplify it, you will get capital per effective labor in the steady state level is going to be equal to saving rate over delta plus g plus n in the power of 1 over 1 minus alpha. It is steady state level of capital per effective labor expressed with all exogenous variables, okay? These are all given: saving rate, depreciation, growth in population, and growth in technology. So now this is steady state level of capital per effective labor. And now we should find the steady state level of output per effective labor, this one, okay? We already know what our output function is, right? Per effective labor, our output per effective labor is equal to capital per effective labor in the power of alpha. So it is going to reach the steady state level if capital per effective labor is going to reach steady state level, which we already found in here, equal. So saving rate over delta plus g plus n in the power of 1 over 1 minus alpha in the power of alpha, right? In other words, our output per effective labor in the steady state level is equal to saving rate over delta plus g plus n in the power of alpha over 1 minus alpha. Okay? This is steady state level of output per effective labor. Output per effective labor. And now the last one, we should find consumption per effective labor in the steady state level, this one. So regarding consumption, you know that output, consumption is equal to 1 minus saving rate times output, yes? If you divide both sides by effective labor, which is going to give you consumption per effective labor is equal to 1 minus saving rate times output per effective labor. So consumption per effective labor is equal to 1 minus saving rate times output per effective labor. Effective labor in steady state level, which is already found, okay? So now you can write from here that our consumption per effective labor in steady state level is equal to 1 minus saving rate times saving over delta plus g plus n in the power of alpha over 1 minus alpha. This is steady state level of consumption per effective labor. Okay? This is it. So during the lecture, we derived three the law of motions and steady state levels, right? The most basic without any growth, with population growth, and with population and plus technological growth. During seminar, we derived three, which means total there are 6 derivations, okay? And not including, we have many more derivations today. Okay? Good? So now I'm erasing the board. Exercise 2. So at the end of lecture, we talked about that golden level of consumption, right? So which means that if we draw the graph, so there is a production function, yes? And we have depreciation, which is usually given. It is not, usually we are not able to control it. It will depreciate, okay? And output function is also given for us. We are following with this depreciation and output function. But there is one factor that totally depends on our decisions, which is saving. So which means that if we are going to just invest, if our investment is very low, let's say just only 10% saving rate, then our investment line will look like this, yes? And the economy will reach this steady state level. If we consider our, to increase our saving rate to 70%, then our investment line will look like this. What happens if our investment saving rate is equal to 1? 100%. So then we will reach this point, yes? This point, where economy is able to produce maximum output. But this maximum output requires 100% investment, which means there is no consumption, which is totally not interesting for us, okay? What is really interesting for people is consumption, okay? So you can see, if investment is low, consumption is somewhere here. If consumption, let's say investment is high, investment rate, we have another consumption which is, relatively similar, right? And in the economy only there is one point, okay? One point or one steady state level, approximately let's see here, which is going to give maximum level of consumption. This consumption, which if saving rate is equal to somewhere here, and it will give us this steady state level, okay? Where our capital is going to reach steady state level in golden level, which is going to produce golden level of output. And what is really gold here is consumption, okay? This is the biggest consumption. Consumption in the steady state, but in golden level, okay? Any saving rate less than this point, okay, is going to reduce consumption. If it's going to be more than this, it will also reduce consumption. Okay? So in the lecture we derived that the economy is going to reach the steady state level if saving rate is equal to alpha. Right? In other words, if we consider our production function as y is equal to capital in the power of alpha times effective labor in the power of 1 minus alpha. We are considering this power. If it's 1 over 2, which is 0.5, our saving rate should be 50%. Okay? Or if it's 1 over 3, which is 33%, it should be 33%. Okay? This is the way we have to find. So this is it. So we proved it without population growth and without technological growth during the lecture. Now we will prove it whether it's really true when there is growth in population and labor. Okay? Let's do it. Our consumption is equal to, our output is equal to consumption plus investment, right? If I divide both sides by effective labor, it will give us output per effective labor is equal to consumption per effective labor plus investment per effective labor. Okay? And our consumption per effective labor is equal to output per effective labor minus investment per effective labor. Now we are interested to find it in steady state level and golden level. This one. In this point, output is also in steady state level and golden level. And investment as well in its steady state level and golden level. Okay? Golden level. So, in here, once economy reaches the steady state level and golden level, right, depreciation line and investment line is going to be, it's going to cross, which is investment equal to depreciation, right? So, now you know that investment per effective labor is equal to in steady state level. In steady state level. Depreciation, delta plus n plus g k hat star. Right? Now there is depreciation, population is growing, and technology is growing. Right? It's equal to this one. So what our output per effective labor is equal to, our production function is given, right? If we divide both sides by effective labor, as we already derived, we will get our output per effective labor is equal to capital per effective labor in the power of alpha. Yes? If we divide. So now, this is equal to this one. And we will, so now if you rewrite it, so consumption per effective labor in the steady state level and golden level is equal to y, which is, it is going to be in steady state level in golden level. If our capital per capita, if capital per effective labor in steady state level in golden level. So now we will place it instead of y, it will give us capital per effective labor in steady state level in golden level in the power of alpha. Okay? Minus, minus. Now we replace instead investment with depreciation, which is equal in steady state level. Okay? And it will give you delta plus n plus g times capital per effective labor in steady state level in golden level. Right? Okay? So, Lord, in the previous derivation, we derived what our capital per effective labor in steady state level is equal to. Right? This equation, this derivation is applicable to any steady states. Okay? In golden level, it's also applicable. So now we will place what our capital in golden level, in steady state level, is expressed in with exogenous factors. Okay? So now if we write it in here, capital per effective labor in golden level is equal to saving rate over delta plus n plus g in the power of 1 over 1 minus alpha in the power of alpha minus delta plus n plus g times saving rate over delta plus n plus g in the power of 1 over 1 minus alpha. So in other words, we can rewrite it again. So our capital per effective labor is equal to saving rate over delta plus n plus g in the power of alpha over 1 minus alpha minus delta plus n plus g times saving rate over delta plus n plus g in the power of 1 over 1 minus alpha. So let us write numerators and denominators separately with separate powers, which is going to give us consumption per effective labor in golden level is equal to saving rate in the power of alpha over 1 minus alpha times, now denominator, delta plus n plus g in the power of minus alpha, 1 minus alpha, right? Minus delta plus n plus g times saving rate in the power of 1 over 1 minus alpha times delta plus n plus g in the power of minus 1 over 1 minus alpha. So now this base for these two is same, right? These bases are same. And now we have powers different. Which has power of 1, which has power of this one. Or in other words, we can write it as what? So now delta plus n plus g in the power of 1 minus 1 over 1 minus alpha. Can I write? Yes. Which is equal to delta plus n plus g in the power of minus alpha over 1 minus alpha, right? Okay? So we will write it like this. So now capital per effective labor in golden level is saving rate alpha over 1 minus alpha times delta plus n plus g in the power of minus alpha over 1 minus alpha minus saving rate 1 over 1 minus alpha times delta plus n plus g in the power of minus alpha over 1 minus alpha. Okay? So now we have this equation given. Okay? We said golden level of consumption, it depends on what? On saving. Yes? So which means the maximum consumption will be reached based on change in saving. So now we will take first difference from this equation with respect to saving. First, in order to maximize, okay? With respect to saving. Yes. So if we take first difference from this constant value, it is equal to 0. Yes? So now alpha over 1 minus alpha times saving rate in the power of alpha over 1 minus alpha minus 1 times delta plus n plus g in the power of minus alpha over 1 minus alpha minus 1 over 1 minus alpha times saving rate in the power of 1 over 1 minus alpha minus 1 times delta plus n plus g in the power of minus alpha over 1 minus alpha. Yes? Okay. Now, this depreciation and this depreciation is same. Because the left side is equal to 0, we can just cancel out these two, right? And now these denominators are same. 1 minus alpha, we can cancel out these two, right? Now our equation is much simple. We can write it as it's 0 equal alpha times saving rate. Saving rate in the power of 2 alpha minus 1 over 1 minus alpha. Right? Minus saving rate in the power of alpha over 1 minus alpha. Okay? So now you can easily find it. In other words, you can write it as saving rate in the power of alpha 1 minus alpha is equal to alpha times saving rate in the power of 2 alpha minus 1 over 1 minus alpha. Yes? If we divide both sides by this factor, then it will give us saving rate in the power of alpha over 1 minus alpha over saving rate in the power of 2 alpha minus 1 over 1 minus alpha is equal to alpha. Right? These two have the same base, so which is going to give us saving rate in the power of alpha 1 minus alpha minus denominator 2 alpha minus 1 over 1 minus alpha equal to alpha. Or it is equal to saving rate in the power of 1 minus alpha over 1 minus alpha equal to alpha, which is equal to 1. So our saving rate is equal to alpha. In order to reach that maximum level of consumption, which is golden level, saving rate should be equal to alpha. Okay? So this is in the case of when we consider population growth and technology. If you try to derive this, just holding the technology unchanged, but allowing the population growth, you will get exactly the same. You will follow exactly the same steps, but only what will be missing is G. Okay? Only G will be missing. This is it. You will get exactly the same. Why? Because once it reaches this step, all of these things will be cancelled out. Okay? So this is regarding our golden rule level of consumption. So now exercise 3. I'm erasing it. Okay. So now we are considering an economy where population is growing by 2% and technology is growing by 4%. So now our growth rate of population is 2% and growth rate of technology is now 4%. This is given for us. What are the steady state growth rates of? Which means that once the economy where population is growing and technology is growing, right? Now this is output function for output per effective labor. Okay? This one is investment per effective labor. This is depreciation. So in the previous case we proved that our capital per effective labor will reach steady state level, right? Once it reaches steady state level, what was it equal to? Our capital per effective labor in steady state level was equal to saving rate over delta plus n plus g in the power of 1 over 1 minus alpha, right? Given, g is given, n is given, okay? Delta is given, it's given. It's exogenous. There isn't anything changing. It's given. It will be same. Which means that our capital per effective labor, once it reaches steady state level, it will not grow. Okay? Which means and output also in steady state level, it will not grow. Consumption instead in steady state level per effective labor, it's not going to grow. Alright? So the first one is, what are the steady state growth rates of capital output and consumption per effective labor? It's equal to 0. There is no growth. Okay? In the first case, growth rate is, let me write it. Growth is equal to 0. There is no growth. It does not grow. But in the second question, what about capital output and consumption per worker? Alright? In the case, now here population is growing, technology is growing. If you refresh your memory, we found during the lecture our capital per worker expressed with this one was equal to technology in discrete time times saving rate over delta plus n plus g in the power of 101 minus alpha, which is this one. Which means that capital is going to grow because technology will grow. Right? So now we are going to find how much is going to grow. We will prove it, okay? We will derive it. So now we have capital output and consumption per worker. I will derive only output per worker, okay? Because the steps are same regarding capital per worker and consumption per worker, you can easily derive by yourself. Okay? So look, our output, number 2. Output per effective labor is equal to what? Output over effective labor. Yes? So now I can write it as 1 over technology times output over labor. Or if it equal to 1 over technology times capital per worker. Right? Or it is equal to capital per worker is equal to capital per effective labor. Oh, sorry. It's not capital, it is output. Output per worker. So, output per worker is equal to output per effective labor times technology. Okay? Let's consider discrete time. We know that our technology for the next year is equal to, because growth is given, right? 1 plus G times technology of today. Or if you would like to find for any years, we have the generalized formula, right? Our technology in the power in T is equal to 1 plus growth rate of technology in the power of T times initial level of technology, which we derived it in our seminar 1. Okay? So we are going to place this factor instead of this 80. Then you will get output per worker is equal to output per effective labor times 1 plus G in the power of T times initial level of technology. Right? So now, I would like you to write this equation for the next period. What about our output per worker for the next year? T plus 1 equal our output per effective labor for next year. T plus 1 times 1 plus G in the power of T plus 1 times initial level of technology, right? Okay. Now we have these two. Now take natural log from these both equations. If we take natural log from both equations, from the first one we will get ln yt is equal to ln y hat t plus t times ln 1 plus g plus ln technology with initial level, right? If we take natural log from this equation, it will give us ln yt plus 1 equal ln y hat t plus 1 plus t plus 1, the power, times ln 1 plus g plus ln a0. So now, if we subtract equation 2 expressed with ln from equation 1, we will get ln yt plus 1 minus ln yt equal ln y hat t plus 1 minus ln y hat t, right? And I'm subtracting this plus t plus 1 minus t times ln 1 plus g. Can I write it like this? Yes. Plus ln a0 minus ln a0. So these two ln's are now equal to 0, right? These t's will be cancelled out. What we have left is ln 1 plus g, right? So if you look here, what ln yt plus 1 minus ln yt is equal to? It is gross rate of output per worker. It is gross rate of output per worker. It will give us that one. Gross rate equal. And what about this one? ln y hat t minus t plus 1 minus ln y hat t. It will give us gross rate of output per effective labor. And plus ln 1 plus g. What is gross rate of output per effective labor in steady state level? 0. It's equal to 0, right? Yeah. Which means that this one is equal to 0. Alright? Which is going to give us our gross rate in output per worker is equal to ln 1 plus g. What is ln 1 plus g is approximately is equal to? As we derived in the first semester, in the first seminar, it's equal to g. Okay? Which means that gross rate of output per worker is equal to growth rate of technology, g. Okay? So which means the answer for y is the growth is going to grow by 4%. Alright? Y will grow by 4%. What about consumption and capital per worker? It will grow by 4% too. Why? How can you derive? You can derive the same. What you are going to change only instead of y, you replace C. Consumption. It will all will be just big C, small c, C, and again you will get that growth rate of consumption per worker is equal to G. You will get same. If you do for capital, instead of case, you will have only, instead of y, you will have only case. Okay? This is your homework. You can do it by yourself at home. It's the same, no difference. The only letter will be different. Okay? Good? So this is in the case of per capita, per worker. Okay? So our per worker factors will grow by technology of 4%. And what about capital stock, output stock, and consumption stock? Total. How So now I'm going to erase it. Okay. So in the second one, we said that our gross, yes, in per capita per worker is going to be 4%. So now again, let's write, I will do just for output itself, okay? Output per effective labor is equal to output over effective labor. Or I can write it as output is equal to output per effective labor times effective labor. So now, let's consider in discrete time, okay? Our technology, we can express it like this, yes? What about our labor? Because it's growing, our labor for any t years is equal to 1 plus growth rate of population in the power of t times initial level of labor. So you can place it in here now. So then you can write it as yt is equal to output per effective labor times 1 plus g in the power of t times initial level of technology times 1 plus n in the power of t times initial level of labor. Right? Or let's rewrite it nicely. So our output is equal to now y hat t times 1 plus g in the power of t times 1 plus n in the power of t times A0 L0. And now I can write it for the next period, as we did in the previous case. Our output for the next year is equal to y hat t plus 1 times 1 plus g in the power of t plus 1 times 1 plus n in the power of t plus 1 times A0 times L0. Now we will take natural log from both equations, which is going to give us ln yt is equal to ln y hat t plus t times ln 1 plus g plus t times ln 1 plus n plus ln A0 plus ln L0. For the second one, ln yt plus 1 equal to ln y hat t plus 1 plus 1 t plus 1 times ln 1 plus g plus t plus 1 times ln 1 plus n plus ln A0 plus ln L0. Now again, we will subtract these two. Second equation from the first. If we subtract these two, we will get ln yt plus 1 minus ln yt, okay, total output equal to ln y hat t plus 1 minus ln y hat t, okay. If I subtract these factors, t plus 1 times ln 1 plus g minus, t ln 1 plus, it will give us
ln 1 plus g.
ln 1 plus g, right? Plus ln 1 plus g. If I subtract these two, it will give us plus ln 1 plus n. ln A0 minus ln 0 is 0. This one is also 0. Okay? what we have left is all this. So now we can write, it gives us gross rate of output equal gross rate of output per effective labor plus ln 1 plus g plus ln 1 plus n. Gross rate in output per effective labor is equal to 0. So gross rate in output is equal to, this is now 0. What our ln 1 plus g is equal to approximately? It's equal to g plus, what about ln 1 plus n? It's equal to n. Okay? So gross rate in total output is equal to gross rate of technology and population, labor. So the answer for the third one is, the answer is 6%. So our y is going, or y, or whether the consumption or capital consumption is going to be 4 plus 2, which is 6%. It will grow by 6%. Okay? If you would like to derive capital and consumption, exactly same. The only change is instead of y it will be capital, instead of y it will be consumption. This is it. No difference. Okay? So this is the alright, exercise 4. Let's start with our exercise 4. So in this exercise, we are given Cobb-Douglas production function, okay? Which is output is equal to capital in the power of 1 over 2 times effective labor in the power of 1 over 2. And now we are given the factor of production, which is growing by 5%. Growth in technology is 5% given for us, okay? 5% growth ratio. And we have growth rate of population given, which is growing by 1%, 0.01. Determine the steady state levels of per effective output and consumption. Given saving rate of 20% and depreciation of 10%, right? So now we are asked to find steady state level of output per effective labor and consumption in steady state level, consumption per effective labor. So now we are asked to find these two factors. We are given saving rate as 20%, 0.2, and depreciation 10%, 0.1. Can we find it? We can easily find it now. Why? Because we already derived all of these steady state levels, right? In order to find our steady state level for output per effective labor, we have to find, first of all, what our capital per effective labor in steady state level is equal to, right? You already know what the equation of this one, right? Because there is population growth and technology growth. So saving rate over depreciation plus growth rate of technology plus growth rate of population in the power of 1 over 1 minus alpha, right? It was the case. So now, if you find this one, saving rate is already given for you, which is 20%, 0.2. Depreciation is 10%, 0.1. Growth rate of technology is 5%, 0.05. Plus, growth rate of population is 0.01, 1%. In the power, 1 over 1 minus, what is our alpha? 1 over 2. Yes, 1 over 2. 1 over 2. Or we can write it as 0.2 over 0.16 in the power of 2. So if I'm not mistaken, if you find this one, it's equal to 1.5625. Right? Is it? Okay. Good. Now, once we found steady state level of capital per effective labor, now we can find easily what our output per effective labor in steady state level is equal to, right? So now, if we divide this function both sides by effective labor, it will give us our output per effective labor is equal to capital per effective labor in the power of 1 over 2, right? If we divide. Or should I write it? So if you divide it, let me write it, okay? So our y over a L is equal to capital in the power of alpha times, I can write effective labor in the power of 1 over 2 over, and now I'm dividing to effective labor, or I can write this effective labor as effective labor in the power of 1 over 2 times effective labor in the power of 1 over 2. Can I? Because if we just get this base 1, it will be equal again 1 to effective labor. Right? So which I can cancel out one of these in here, which is going to give us, this is 1 over 2, sorry. Right? Capital over effective labor in the power of 1 over 2. And it's equal to capital per effective labor in the power of 1 over 2. This is 1 over 2, sorry. So it's same. So once we got it, we can easily find what our output per effective labor in steady state level is equal to. It's equal to capital per effective labor in steady state level in the power of 1 over 2. And it's equal to 1.5625 in the power of 1 over 2, or it's equal to 1.25. Okay, good. Now, regarding consumption per effective labor, it's equal to 1 minus saving rate times output per effective labor in steady state level. Our saving rate is given, which is 20% times 1.25, which is equal to 1. Yes? Okay. We quickly found it. Now next one. What happens to per capita output and per capita consumption? Yes. So now we found the steady state level of capital per effective output, consumption, and capital, right? What about per capita, per worker? What will happen to per worker output, per worker capital, and per worker consumption? From the previous derivations, we made sure that once the economy reaches steady state level in per effective labor, economy will not grow. But per worker is going to grow by growth in technology, right? It will grow by 5%. This is the answer. Because we already proved it in the previous exercise. Right? It will grow by G. Next, look, suppose now that the government wants to raise welfare and they will start an education reform which raises G, technology, from 5% to 10% at zero costs. So, if you graphically draw it, you will get that, let's say, production, investment, depreciation. Yes? Production, function, depreciation. Okay. So look, let's say the economy reached steady state level, this economy, where saving rate is 20%, depreciation 10%, growth and population and technology is given. It reached this level, okay? It reached this level. Let's suppose. At this point, growth stopped, yes? Yes? Okay. So now, we are saying that, that is there any possibility to make a reform without any cost? It's impossible, right? But this is assumption that it's possible. Let's say, today the growth in technology was 5%, but the next day we woke up, it just happened to become 10%. All right? We were given that gift. So if it happens, here our question is asked, what are the short and long run effects? It's of, of per capita production, on per capita production, output, consumption itself, and per capita consumption of this change. Okay? As we already proved previously, if let's say if it's in steady state level, if it was growing by 5%, if next day it's going to be by 10%, they are going to grow by 10%. Same. But what about consumption itself? This big C.
No, it's short term. Growth and population.
Right. So it will grow by growth rate of technology and plus growth rate of population, which is 10% plus 1%, which is equal to 11%. Okay? What?
Should be 5.
No, we said it's now 10%. It changed, right? 11%. Okay. What do you conclude about the success of education reform, Lord? Let's suppose here that there must be incurred some cost, yes? Just ignore it, it's not true. It's not impossible to without any cost. If government wants to make government that educational reform, then government should spend money for education sector, yes? Which means that government is going to increase consumption. And it's going to reduce investment. Right? If it's the case, then investment is going to be like this because investment rate is less, which we expect that the economy is going to reach another steady state level, right? But this consumption that government is increasing in order to invest it to education, as if it is investment, okay? But it is very effective investment. Why? Once government, there are many cases, many developing countries, right, that hire, universities and all, they're very corrupt. Okay? So now government in our country, what's happening now, reform is going on, right? Especially for education sector in order to improve it. If we are going to improve it, right, government is spending, now we are bringing better professors, whatever. As a result, we are producing better students, okay? Those students, there is highly likelihood they will become scholars, scientists, okay? Which are going to invent something. If they are going to invent, they are becoming stronger because of this more investment, right? So now our Y is equal to technology times capital in the power of alpha times labor in the power of 1 minus alpha, right? Now we are saying this technology is growing, right? If it was 5%, but because of government intervention, now it became 10%, right? Even though in the short run, if it's going to slow down, yes, because government, investment, but it will change this technology. There will be some, good scholars which are going to invent some technology. As a result, this technology may double. If this technology doubles, then output will double. Investment will double. Everything will double. Do you understand? So therefore, reform in education is very important thing. Okay? Which is going directly affect to this technology. This is the most important thing in here. Capital may grow, labor may grow, but this sudden growth of technology, it will really change the life of all people. Okay? So exercise 5. Again, we are given very simple production function. Okay? Let me erase it.
Just signal.
production function is given for us, which is output per worker is equal to capital per worker. Capital per worker in the power of 1 over 2. So what is the technology in here now? Technology is equal to 1. Alright? So if you want to write it in aggregate form, it's like output is equal to capital in the power of 1 over 2 times labor in the power of 1 over 2. Where is this technology B is equal to 1. If you divide both sides by labor, you will get this one. Okay, it's the same. And now we are given growth rate of population, which is 5%, okay? 0.05. And we are given saving rate, which is 30%, right? And we are given depreciation rate, which is 1%, 0.01. We are asked to define the steady state levels of per capita output, capital, and consumption. Can you define? Now there is no growth in technology in here. Okay. So now we should find steady state level of capital per worker, where population is growing, which was equal to saving rate times technology in your notes, okay, over delta plus growth in population in the power of 1 over 1 minus alpha. It was like this, right? So where you can easily, you have everything given here. Saving rate is 30% times technology is equal to 1. Depreciation rate is 1%, 0.01. Population growth is 5%. In the power of 1 over 1 minus 1 over 2, yes? Alpha is 1 over 2. Which is equal to, if we divide this one, it will be 5 squared, which is 25. Okay? It's equal to 25. And regarding output in steady state level is equal to, where it's going to reach steady state level if our per capita capital is steady state level, which is 25 in the power of 1 over 2, which is equal to 5. And regarding consumption, the last one, is equal to 1 minus saving rate times output in the steady state level, or it's equal to 1 minus 0.3, 30% times 5, which is equal to 3.5. Yeah. So this is regarding consumption in steady state level. Okay, this is very simple one with the right. This one is important question, okay, which we haven't practiced yet. Using the given detail of everything, okay, find the golden rule level of consumption. Is it golden rule level of consumption 3.5?
No.
Why? Because our saving rate is not equal to alpha. In steady state level, in golden, right? In golden, to reach that golden, our saving rate should be in golden level. With golden level should be equal to alpha, which is alpha is equal to 1 over 2, or it's equal to 0.5. This economy, in order to reach golden rule level of consumption, golden level of consumption, it should increase its saving. It should be 50%. Okay? So, which means, in order to find consumption in golden level, it's equal to 1 minus saving rate in golden level times output, okay, in steady state level in golden level. In order to find it, first we have to find what our y in golden level is equal to, right? In order to find our y, we should find what our capital in golden level is equal to. Yes? So now we have to find our capital in steady state level in golden level. Okay? It's equal to saving rate in golden level times technology over depreciation plus growth in population 1 over 1 minus alpha, which is equal to, what is golden level of saving rate? 0.5. 0.5, technology is 1, depreciation is 1% plus population is 5%. So 1/1 minus alpha of 1/2, which is equal to, you will get it's equal to, if I'm not mistaken, 69.44. Is it? I think you will get this number, okay? So this is it. If you find per capita, right? In steady state level in golden, you now, our per capita in steady state level gold in the power of 1/2, right? Which is equal to 68.33. And now last thing that the most important is consumption. Steady state golden level is equal to 1 minus saving rate in golden level times our output in golden level per worker. So here 1 minus 0.5 times 8.33 is equal to 4.17 approximately, right? So this economy is going to reach maximum consumption of 4.17 if it's going to increase its saving rate by 20%. Okay? So look, next one. Demonstrate this one so in Excel spreadsheet. You asked to do it in Excel spreadsheet. I will quickly show you, alright? I will quickly show you. So now if you open this Excel sheet, okay? So now let me make it bigger so you can see. So now our population growth is 5%, 0.05. Our saving rate is 30%, right? Depreciation is now 1%. Let's say our initial capital is 1, measured in billions, okay? 1 billion. 1. Our output, how do we write that function? Our output is given, right? Is equal our capital. It has the power of 1/2. And consumption is equal 1 minus saving rate, yes, which is 30% constant, times output. And investment is equal saving rate, which is 30%, keep it constant, times output. Right? And now depreciation equal. Depreciation is given 1%, which is constant, plus growth in population, again it's constant, okay, times capital. And what about change? This is the most trickiest part, okay, this one. Now here you have to use change, which is derived at the law of motion, derived in discrete time, not continuous time, okay? Because that in continuous time, that change in per capita capital it was equal to investment minus depreciation, right? It was like this. We derived it. Only if there is population growth. But if it's derived in discrete time, it was looking like this. T plus 1 minus T change was equal to 1/1 plus N. Say investment minus depreciation. It was looking like this. So this factor is very important in here, okay? If you are not going to consider this one, this economy will not reach steady state level. So therefore, now if we consider that one, it's equal to 1/1 plus depreciation, right? Oh, population growth, which is constant, okay? times investment minus depreciation. This is the change, okay? Now this is the correct way of finding change. Now is, for the next year, it's equal to our last year capital plus change, yes? If you find for these years, and you apply it for all years, okay? Now I found data for all years. If you just check, then you will find country reached that steady state level, okay? Where capital is 25, output is 5, consumption is 3.5, as we derived first, right? Okay. And then we made argument that if we are going to change saving rate from 30% to 50%, then we will reach maximum consumption. Yes? Golden level. So where is 4.16, right? So now let's try to increase more investment. Now you can see here output is 69, capital is 8.3. Oh sorry, capital is 69 and output is 8.3. Now if you change saving rate from 50% to 60%, 0.6, okay? Now you can see capital increase, which was 69, now it's all 100. Output is 10, but consumption decreased. It was 4.16, okay? So therefore, it's the only point where it will be the maximum, which is 4.16, okay? This is the way you can derive it in Excel spreadsheet, okay? Good. So last exercise for today. Last one. I'm erasing it. Alright, Pythagoras production function is given for us. Y is equal to capital in the power of 1 over 2 times labor in the power of 1 over 2. We are given saving rate as 30%, right? Depreciation rate is 5%. Depreciation rate is 5%. Delta. Depreciation rate is 5%. But growth in population depends on per capita income. So now it tells us that countries with low income, okay, their growth rate of population is 10%. And countries with high income, their growth rate of population is 5%. Okay? If the economy, if it's poor country, growth rate of population is 10%. Rich economy, 5%. Is it true?
Yes.
It is true, right? It's indeed true. Why those countries are rich? One very important reason is because females also are economically active in that economy. If females are working economically active, it means that having birth rate will be less. Okay? Because it's one labor factor it really affects. It's one factor, there are many others. Okay? Good? So now we have this one. Determine the steady state levels of per capita capital output and consumption for both low and high income countries. Can you find? You can now easily find, right? Because it's, again, there is no change in technology, just ignore it. So steady state level of capital per worker is equal to saving rate times technology over delta plus growth in population, 1 over 1 minus alpha, yes? If you find for low income country, steady state level of capital for low income country is equal to, what is saving rate? 30%. Technology is 1, yes? Depreciation rate is 5%. What about population growth? 10%. 0.1. 1/1 minus 1/2. And it's equal to, it will give you 2 in the power of 2, which is equal to 4, yes? So now you can find output in steady state level for that low income country, where 4 in the power of 1/2, which is equal to 2. If you find consumption for low income country, which is equal to 1 minus saving rate is 0.3, yes, times 2. That out, which is equal to 1.4. And you find it for high income country. This is for low income country. If you find steady state level of capital for high income country, it's equal to, saving rate is 0.3, technology is 1, depreciation is 5%, but population growth is now 5%. So in about 1/1 minus 1/2, which is equal to, if you find it, 9. It's equal to 9. Yes, it's equal to 9. If you find y for output per worker for high income country is 9 in the power of 1/2, which is equal to 3. And consumption in steady state level for high income country is equal to 1 minus saving rate 0.3 times 3, which is equal to 2.1. 2.1. Okay? 2.1. Good. We are done with it. So now let's graphically plot it in the graph. If we plot it in the graph, our output now for high income country is, capital is 9 in steady state level, right? And when it's 9, output is equal to 3. 3. And for low income country, capital is somewhere here 4, right? And output produced for this with this one is 2. Right? Production function for both is same. So that production line for both countries is same, because function is same. Right? So this y is equal to capital 1/2. This is that. So now we are saying that once economy reaches that steady state level, consumption is equal to 2.1, right? For this economy, 2.1. So, which means that that depreciation line of this country, yes? Where investment, how about that investment curve? Is it same for both countries?
No.
It's same, why no? Because saving is same, right? It's same, so which means that it will look like this, right? Look like this. It's same. So this is now the, but in here now for a country with low income country, their depreciation line is different. So now their depreciation line looks like this, right? Because here is depreciation plus population growth of 5% only, while in here it is depreciation plus population growth of 10%, which is going to make it steeper, right? So this now, consumption is equal to 1.4, right? 1.4, okay, good. Now here is the question. Next, suppose the economy is initially in steady state level with population growth of 10%. This country, low income country, okay, low income country, they reach this steady state level. which means that after this point, life is not going to change. Let's say this consumption per worker is per day is $1.4, which is absolute poverty. Let's suppose. Okay? So now, government, that research was conducted by demographers, okay? Research. And according to that research, it shows that if output for low-income countries reaches 2.5 units, if output reaches 2.5 units, people automatically reduce their birth rate by 50%. Okay? That type of assumption. So which means that in order to make output to that 2.5 unit, which is now 2, more females should be economically active, they should be more educated, which is all is going to reduce population growth. Okay? So now it is the case. Alright? It's the case. So here's another argument. So now the World Bank decides on development program for this country. Sustainable development goals, number 1 is no poverty, right? How big does the help package from World Bank need to be in order to be effective in the long run? So now World Bank knows if we are one problem in those poor countries is high population growth. 10% growth is unimaginable. Okay? So that they know that if they are going to help this country to make their output reach 2.5, population growth will decline to 5% from 10%. So in order to make it 5, are they able to make it to reach that 2.5 with capital of 4? No, right? With given, they are able to reach that 2 only. So now in order to reach that 4, how much do they need? Capital. This is given for us, yes? For low income, which is now in order to make it 2.5, our capital should be equal to 6.25. Alright? This low income country needs capital of 6.25 in order to make it 2.5, which is not available. How much do they need? It is 2.25. So now if World Bank provides them 2.25 help package of capital, then economy at this point they will be producing this much, okay? And depreciation line which was in here, 10% will shift to this line. Because it's no more 10%, but it's now 5%. It will shift. Do you understand? So once it shifts, then economy again starts growing and it will reach this point. This much of consumption. Okay? And the last question, what happens if the per capita capital transfer is less than required? Let's say World Bank, instead of providing 2.25, they said, okay, just 2, I think it's enough. They provided 2 and it's now 6. Which means it is lower than 2.5, right? Are they willing to reduce birth rate? No. The condition is 2.5. So now, if it's going to be less than 2.5, at this point, people will be consuming more, but depreciation is greater than investment, right? Which means that the economy will go back again to its initial steady-state level. They will be temporarily having more, consuming more, but end up again to that old position. Okay? So our seminar is over. Now you can go.